Hi there, this is Ms. Page, and in this lesson we're going to be talking about how to solve trigonometric equations, which are equations that involve at least one trigonometric function. And we're going to look at equations that have what we call a linear structure or a quadratic structure. And if they have a linear structure, meaning that the trig functions are to the first power, that's the highest power, then we do similar things such as when we solve a linear equation and use our undoing algebra to get the trig equation or the trig function rather isolated. If we have a quadratic structure, which means that we're looking at having a power of 2 on a quadratic function such as sine squared, then we use quadratic structures, getting into standard form and trying our factoring, or we might be able to use the square root property strategy, things like that. Another thing we want to talk about before we start solving some equations is understanding that the range of values for our sine and our cosine functions is restricted, and we can look at our unit circle to see this. Remember that x is cosine and y is sine, and for our unit circle values, the smallest x we have is -1, and the largest x we have is +1, and those would be the smallest and the largest values for cosine of an angle. So what we're looking at here is understanding if we had the cosine of an angle, call it theta, that was equal to 2, that would not actually give us any angle values because 2 is larger than 1. And according to our unit circle, the largest value we can have for cosine of an angle is 1. Same thing would be true for cosine that was equal to, say, -2. That's smaller than -1, and -1 is the smallest cosine value. So there are no angles in those situations. Same thing is true for sine. In our unit circle, remember, sine is y, and the smallest y we have is -1, largest y we have is +1. So same thing is true for sine. If I had sine of an angle equals 2, that's too large, bigger than 1, that's not going to give me an angle. And if I had sine of theta equals something like -2 being smaller than -1, there's not going to get an angle there either. All right, let's take a look at an equation. So one of the things that you want to be aware of is when you're solving trig equations, how you're actually solving them. We are going to look at focusing on solving over the interval from 0 to 2 pi radians, which means that our answer should be in radians and in that first positive revolution. And notice too here that in our interval the bracket is with the 0 radians. So if we're in that position, we should use an answer of 0 radians, not 2 pi radians, which is a coterminal angle to 0. So here in this equation, we are looking at a linear structure because the highest power of sine is the first power. So I would treat this similar to how I treat the equation x plus 2 equals -x. I might add x to both sides and then subtract 2, and that gives me 2x equals -2, and so on and so forth. So in a trig equation with a similar structure, I would add, this is -1 sine x, so I would add sine x to both sides, and I would subtract the square root of 2 from both sides. So this is 1 sine plus 1 sine, so that's 2 sine of x equals -square root of 2. And then I'd undo that multiplication there, dividing both sides by 2. And I get sine of x equals -square root of 2 over 2. So now I need to know my unit circle and what angles have a sine value of -√2 over 2. And the √2 over 2's, remember, positive and negative have to do with our fourths, which are the angles that have a reference angle of 45 degrees. So we need to realize there will be two quadrants rather in which sine is negative because sine is y, and those quadrants would be quadrant 3 and quadrant 4, which means we're going to have two angle answers. So they'd have to be the fourths. They're in the third quadrant and the fourth quadrant, which would make them the 5 pi fourths and 7 pi fourths angles, like so. All right, there's a practice problem here next. So I want you guys to pause the video, give this one a try, and then turn the video back on when you're ready to check. All right, let's take a look here. So similar, adding cosine to both sides gives us 2 cosine x equals 1, and then dividing by 2 gives us cosine of x equals 1/2. So then we have to know our unit circle. Where is cosine value equal to 1/2? At what angles is cosine 1/2? There again, 2 quadrants where cosine is positive. Cosine, remember, is our x coordinate. So it'll be quadrant 1 and quadrant 4. And cosine is 1/2 at the third. So as you can see, we have the pi thirds in the first quadrant and the 5 pi thirds in the fourth quadrant. All right, let's take a look at this problem together. So here we have 3 times tangent squared x minus 1 equals 0. This would be a quadratic structure because our trig function of tangent is squared. And so we would treat this problem very similar to how we do something like 3x squared minus 1 equals 0. This one, we can't factor because we don't have a difference of 2 squares, but we can isolate the x squared by adding 1 and dividing by 3, and then take the square root of both sides. And that's our square root property, and remember that would give us a plus or minus. And then we can simplify and stuff like that. So we treat it very similar to that, except we have tangent instead of just an x. So we would add our 1 to both sides, then divide both sides by the 3. So now remember, tangent squared x means tangent times tangent, or tangent of x squared. So when we square root the tangent squared x, then what's happening is the square here and the square root there cancel each other out as inverse functions and leave us with tangent x. It'd be like taking the square root here, those go, we're left with tangent of x. We also have to take the square root of this side, of course, and that gives us a plus or minus the square root of 1/3, which would be plus or minus the square root of 1 over the square root of 3, and the square root of 1 is 1. So we get plus or minus 1 over root 3, and that would give us then tangent of x equals plus or minus the square root of 3 over 3 when it's rationalized. Now, being tangent, this problem is a little more challenging because tangent, of course, is not directly part of our unit circle. So what we have to do is look at our quotient identity, sine over cosine for tangent. So we're looking at sine of x over cosine of x for tangent. And we're trying to figure out what ratio of sine and cosine would simplify to this root 3 over 3 or to 1 over root 3 before we rationalize. And so you can, and if you're not sure, try one in the first quadrant. Okay, try an angle with the ratio of sine and cosine, see what happens, see if it matches. If it doesn't match, move on to something else. So, for example, let's say I take my pi 6 radians. Sine of pi 6 radians is 1/2, and cosine is root 3 over 2. If I simplify this, this would be 1/2 times the reciprocal, which would be 2 over root 3, and notice the 2's would reduce, and that would give us 1 over root 3, which does match that. So that's telling me my angles are where my sine is both positive and negative 1/2. Now sine is positive in 2 quadrants, first and second, and it's negative in 2 quadrants, third and fourth, which means that we're dealing with 4 angles that will give us the positive and the negative. And so in the first quadrant, we're looking at pi 6. Second would be 5 pi 6. Third quadrant, 7 pi 6, and the fourth quadrant, 11 pi 6. So we get 4 angles as our solutions. All right, we're going to try a practice problem. Pause your video here, give this one a try, come back when you're ready. All right, let's take a look at the solution here. So adding 3 and dividing by 4 gives us sine squared equals 3/4. Then we take the square root of both sides. This is the same thing as taking the square root of sine of x quantity squared. So the square and the square root cancel. And then this is the square root of 3 over the square root of 4, and the square root of 4 is 2. So there's no need to rationalize here. So now we need to know, well, what angles have a sine ratio of either positive or negative root 2, or square root of 3 over 2 rather. And that's again going to be all 4 quadrants. And those are our thirds, as you can see. So pi thirds in first quadrant, 2 pi thirds in second, 4 pi thirds in quadrant 3, and 5 pi thirds in quadrant 4. All right. Let's take a look at this one together, another example. So here we have cotangent x times cosine squared x equals 2 cotangent of x. And so this is a quadratic structure also because the cosine is squared. Be very careful here. Remember that you cannot use any kind of algebra strategy that divides by an expression that involves x. And that includes cotangent x. So you can't divide by cotangent of x here. All right. What we actually have to treat this as is similar to an expression where we had, let's say, xy squared equals 2x. And getting it into its standard form, we would subtract the 2x, and then x is a common factor, and we can separate x and y squared that way. And that would be like how we're going to separate then the cotangent and the cosine squared. So what I'm going to do here is subtract this cotangent of x. So I have cotangent of x times the cosine squared of x minus 2 cotangent of x equals 0. And as I said here, cotangent of x is a common factor of GCF, so I'm going to factor it out. And that would be times in parentheses cosine squared of x minus 2. So now I have a product of factors equals 0. And remember, when we create a product of factors equals 0, our next step would be to use our zero product property. So either cotangent of x equals 0 or cosine squared x minus 2 equals 0. So for cotangent of x equals 0, again, similar to the tangent problem, since cotangent is not directly part of the unit circle, we'd use a quotient identity. Cotangent is cosine over sine. And in order to be 0, then our denominator has to be either actually technically 1 or -1, because there are two places where cosine is going to be 0, and those angles are going to be our quadrantal angles of pi halves radians and 3 pi halves radians, like so. For this one, we would add 2 to both sides, giving us cosine squared x equals 2, and then undoing our power of 2, we would take the square root of both sides. And so now we need to know, well, what angle would have a cosine value of either positive square root of 2 or negative square root of 2. All right, here's again where number sense is helpful, since these would all be no calculator problems. So we have to know our unit circle, and we have to recognize that square root of 2 is actually larger than 1, and it's about 1.4. So square root of 2 is larger than 1, and the unit circle shows us that the largest value of cosine is 1. And so there is no cosine or no angle that has a cosine that will be square root of 2. It's too big. And negative square root of 2 is about -1.4, and that's smaller than -1, which is the smallest value of cosine. So there's no angle that's going to have a cosine of negative square root of 2 either. So this gives us no extra angles. We just have those two right there. All right, let's try a practice problem. Here you go. Give this one a try. Pause the video. All right, let's take a look at the solution. So similar to the previous problem, we're looking at getting standard form equal to 0 by subtracting 2 sine of x, then recognizing that this would be like sine of x quantity squared, so sine of x is a common factor, and it gives us this, and then zero product property gives us those. So where sine is 0 is at 0 in pi radians, and here we have to realize, again, 2 is larger than 1, and 1 is the largest value of sine, so there's no angle that is going to have a sine of 2, so that gives us no other angles. If you said 2 pi radians here, again, be aware, in the interval, the bracket is with the 0, meaning that's included in the interval, but the parenthesis with the 2 pi means don't use that one. All right. Here's another practice problem. Give this one a try. Did I skip this one? Oops. Yes, I thought something was off. All right, let's take a look at this one. You're not ready for that other practice problem. Not quite yet. All right. So here, what we have is a quadratic structure again, because the power of sine in that first expression, first term, is squared. So, but this is not standard form because we're equal to 1, not 0. So don't treat sine as a common factor here. Wouldn't work that way. This would be like 2x squared minus x equals 1. We'd subtract 1 from both sides and then get a trinomial structure and then factor that trinomial structure. That is what we are looking at doing. So we'd have 2 sine squared x minus sine x minus 1 equals 0. And then this would factor into 2 binomials. So this right here, we'd have a 2 sine x and a sine x. So 2 sine x times sine x would be 2 sine squared x. And then we'd want a minus 1 here and a plus 1 here. That'll give us a negative 2 sine x plus sine x for that negative sine x in the middle. We have a product of factors now equals 0. So 0 product property next. So here we'd subtract 1 and divide by 2. So we have sine of x equals negative 1/2. We want the angles then where sine would be negative 1/2. Sine is negative, y is negative in quadrants 3 and 4. And the 1/2s come from our angles that have a reference of pi 6. It's our sixths. So we want the sixth ratios in our third and fourth quadrant. So those would be the angles of 7 pi 6 and 11 pi 6. And then here we'd add 1, so we have sine of x equals 1. So here we have to know, well, what's the angle that has sine of 1? And that is our quadrantal angle of pi halves radians, 90 degrees. So we get 3 angles this time. All right, now that practice problem. Here you go. Pause the video and give this one a try. All right, let's see what we've got here. So this time you have to subtract that 3 cosine of x from both sides, and hopefully you realized it had to go in the middle so that you had a structure, a descending order of power structure, similar to 2x squared minus 3x plus 1 equals 0. And then you're factoring it. So instead of a 2x and an x, in place of your x's, you have these cosine of x's. And then your 0 product property. And then that gives you either cosine of x has to be 1/2 or 1. Our unit circle tells us cosine, which is x, is positive in quadrants 1 and 4. And cosine, the 1/2s for cosine go with our thirds. So we have pi thirds in the first quadrant and 5 pi thirds in the fourth quadrant. Cosine is 1 at 0 radians. Again, don't use 2 pi because, again, the interval says include 0, don't include 2 pi as an answer. And so we use the 0 radians, which gives us those 3 angles. Here is another practice problem. Pause the video and give this one a try. All right, let's see what we've got here. So this one, again, we would get it, it's a quadratic structure because cosine is squared, so we get it equal to 0. This one we do have a GCF here of cosine x, 0 product property, and then here cosine of x being 0, we have, it is at our quadrantal angles of pi halves and 3 pi halves, which are 90 and 270 degrees. Here we'd add the square root of 3 and divide by 2, so now we're looking at what angles have a cosine of root 3 over 2, and those are our 6's in the first and the fourth quadrant where x is positive, cosine is positive. That's your 11 pi 6 and your pi 6. Notice here they're written in order from least to greatest. That is something you want to consider. We've talked about that, and it can definitely be something that comes up when you're looking at listing angles in radian measure. So think about moving around your unit circle in the counterclockwise positive direction and what angle would be before other angles. All right, that is the last practice problem here. So you can now give your assignment a try. Have a great day.